Hello, everybody, and welcome to Fiske Planetarium Science Under the Dome series. This month's facilitator is Amy Schechter. Go ahead, Amy, and take it away.
All right, thanks. Hello, and thank you all for tuning in to Fiske Planetarium's virtual Science Under the Dome talk series. My name is Amy Schechter. I'm one of the lead facilitators for Science Under the Dome and also a second-year Ph.D. student studying astrophysics here at CU Boulder. As a reminder, we will continue to provide high-quality online videos until Fiske Planetarium is able to safely reopen. And of course, be sure to drop any and all questions in the chat, and we will address them during the Q&A at the end of the show. Our speaker tonight is Jimmy Negus. He is a lead facilitator for Science Under the Dome and is currently pursuing his PhD in astrophysics here at the University of Colorado Boulder. He earned his BA in physics with a specialization in astrophysics from the University of Chicago in 2013. Here at CU, he analyzes the properties of active galactic nuclei, which are supermassive black holes that consume nearby matter. In his spare time, he enjoys stargazing, riding his motorcycles, and volunteering at Fiske Planetarium. He has also authored 2 books, Mysteries of Space, Black Holes Explained, and Mysteries of Space, Supernovas Explained. And also joining us this evening is our navigator, Fiske Education Assistant, Jeremy Osowski. This evening's talk is titled A Crowded Orbit, the Coevolution of Satellites and Space Junk. Less than a century ago, human instruments first ventured onto the dark shores of space. Fueled by scientific curiosity, nationalistic fervor, and technological innovation, we have since expanded our presence in space at an unprecedented rate. In the process, have we adversely impacted our local space environment? Where do all of our retired rockets and dead satellites end up? Does space junk threaten the survival of astronauts on future missions? Space junk or space debris refers to any non-functional human-made objects in space orbiting Earth. These range from sub-centimeter paint chips to 18-ton empty rockets. Join us this evening as we explore our planet's orbital graveyard. Jimmy will begin by tracing the evolution of human spacecraft and instrumentation, delve into its waste products, and finally explore sustainable paths forward. So with that, Jimmy, please take it away.
Awesome. Thank you so much, Amy. I want to thank you and Jeremy for all of your support in preparing for this talk. We begin our journey this evening far from home, or perhaps for some, right at home. A whisper from that great beyond faintly reminds us of our origins. Its dim lights glow softly, like distant beacons. Vibrant stars radiate and glisten. Massive galactic structures slowly drift. Unexplored worlds process beneath the veil. Spawned from the seeming abyss, the web only grows in complexity, enriching the grand tapestry with hues of violent destruction and wondrous creation. For eons, our universe has sprawled its polychromatic essence onto this dark canvas. And the awe of its mysterious yet tantalizing nature threads our human history. How fortunate our species has been to glimpse its evolution from a small remote rock cast deep within a tiny crevice of the Milky Way. From Earth, we have gazed up for millennia, and for millennia, the night sky has gazed unto us, indifferent to all of our differences. Now, the beauty of astronomy is unlike many sciences. You don't need a microscope. It only takes your human eyes to appreciate and to study the wonder of it. As such, scholars predict that the first astronomical observatory was built nearly 7,000 years ago in Africa, somewhere in the arid Nubian desert. 2,000 years later, we find evidence that ancient Chinese and Indian astronomers used the night sky to track the passage of time and to create calendars. It wouldn't be long before the first star catalog was assembled in Babylonia. Even more fascinating to me, the ancient Egyptians. They used the stars to create sacred landscapes with the pyramids. They envisioned deities and spirits occupying the ethereal realm of the night sky. we may never know the true extent of their astronomical knowledge or the connection they had to the cosmos. And as we learned more about the position of these stars throughout human time, we learned how to leverage their positions. We used them to navigate and to chart the land and the seas. Using the northern star Polaris, we even used it to escape the maws of slavery with the Underground Railroad. As our technological capabilities further evolved, we would go on to build the first astronomical telescope, develop a heliocentric model of our solar system, which placed the sun at the center. And we identified solar system planets and their moons. During the process, we even established a law of universal gravitation. By 1930, our single species on this remote rock had calculated the expansion rate of the entire universe, which is just a mind-boggling feat. But at this point, we still remained confined to our planet Earth. And more precisely, we remained submerged beneath its atmospheric depths. But as we learned more and more about our universe, the possibility of venturing further to seeking the uncharted domains of space became more and more intriguing. But before we can talk about our venturing into space, it's critical to know, what is space? Where does it begin? Is it an arbitrary point? Well, let's look at the atmospheric layers of our planet to understand where space truly begins. Now, the first layer is probably most familiar to many of us. It's the troposphere. This is where all of our weather systems occur. So tornadoes, hurricanes, they all develop within the troposphere, which extends from the surface of our planet to about 20 kilometers or 12 and a half miles up. You're in this region anytime you take a commercial flight to visit family. Next is the stratosphere. So this is where the highest jump was ever recorded. Let's take a look at Alan Eustace in his terrifying journey through the stratosphere. You can really perceive how far up he is. And this jump was actually at about 40 kilometers, or about 25 miles above our Earth's surface. It's also too important to acknowledge the ozone layer resides here. This layer is critical for our planet's habitability. This blocks extremely harsh UV radiation from the sun. As we venture further, we enter the mesosphere, and this is where meteorites burn up due to the friction caused by atmospheric gases. So I can hear some of you saying, are we in space yet? We're getting there. We'll need to ascend a bit higher to get there. And we enter here the thermosphere, which is 85 to 600 kilometers, or 53 to about 375 miles up. This is the region we're most interested right now. This is where space officially begins. And what you'll notice highlighted in the center of the image at the top is the Kármán line. This is the official boundary of space. It's 100 kilometers, or about 62 miles above sea level. For those of us that live in Colorado, this is equivalent to roughly the distance, the round trip distance from Denver to Boulder. Now, this is not an arbitrary designation for space. There's actually some calculations involved. And it turns out this is the point where the atmosphere becomes too thin to support aeronautical flight. Literally, a vehicle would need to travel faster than its orbital velocity to sustain sufficient lift. So this is what is internationally agreed upon as our official boundary into space. And finally, as we go further up, we get to the exosphere. And this ranges from about 600 kilometers to 10,000 kilometers, or 375 to about 6,200 miles. Once you're in the exosphere, you're really beginning to get further into space. So now we have a sense of where space actually begins. So let's return to the early 20th century. where our astronomical acumen was really beginning to grow and the lure of space travel was becoming tangible. At this point, maybe the Earth's surface was just growing dull for many. And maybe that was the case for the Wright brothers. As you can see on the image on the left, the first flight of the Wright Flyer occurred on December 17th, 1903. This was the world's first motor-operated airplane. Now, its flight was not impressive. It only flew 120 feet in about 12 seconds, going a very fast 7 miles per hour. However, the key takeaway here was not just blueprints to build a basic airplane. What the Wright brothers instilled in our global culture was the possibility of flight. How far could we extend upon their initial foundation? And over the following decades, as we would suspect, there were several advancements in flight technology and aerodynamics research. Now, this culminated not just in what we're most familiar, which is the Apollo program, but what preceded it was the Bumper program. And most importantly was the Bumper 5, launched February 24th, 1949 from White Sands Missile Range. It was the first human-made object, according to NASA, to enter space. And it actually reached a height of about 403 kilometers, which is well over the Kármán line, and for reference is roughly about where the ISS orbits. Now, this mission actually had some science involved. The instruments on board measured temperature and cosmic ray impacts. So this wasn't just sending an instrument up, but this was really the first time we conducted science in space. But if you dig a little bit further, you'll find a less discussed MW18014, a German rocket launched in Germany on June 20th, 1944. It reached a less impressive height of 176 kilometers, but as of our present day boundary of space, this was officially our first vehicle to go beyond the Kármán line and to actually breach space. Now, this had less science. It was purely a vertical test, and it really wanted to test how high a vehicle could go at the time. So this was really just a proof of concept test. Nonetheless, humanity's first steps were truly imprinted onto the cosmic shore. As you can imagine, these remarkable pioneering flights catalyzed the urge to delve further into space. With a glimmer of what was possible with Bumper and MW18014, the prospect of possibly having an instrument achieve orbit was too enticing to be denied. The next unexplored corridor of our civilization was becoming apparent. As we had explored most of its surface, the sky was the next natural location. Would this newfound inspiration to tread deeper into the celestial waters be rooted in uniting our species, or better comprehending the depths of our origins? Maybe we could continue the legacy of our early inhabitants and embrace the cosmos, become wise, find a way to become an unfragmented species. Or maybe develop instruments that could benefit all of humanity. Or would the conquest for political and technological dominance supersede? While many nations were contributing to our global knowledge and likely pondering the same cosmic depths, to the US and the Soviets, the world probably looked something like this. And Sputnik 1 would provide an immediate answer to the inquiries I just posed to you. 183 pounds, built by the Soviet Union, launched on October 4th, 1957. This, Sputnik 1, would be the first satellite to orbit Earth at a height of 250 kilometers. Now, it would fall back down to Earth on Christmas Day of that year, but while it was up there, it did conduct some radio observations and was able to determine electron density as well as some temperature measurements. So surely this was a scientific endeavor, no? Well, not quite. You see, there was no global celebration or global parade for this feat. Sputnik was launched out of fear that the US would launch a satellite first. And as I've learned, you can never truly disassociate the means from the ends. To the US, their thinking was, could the Soviets use this technology to launch rockets at us? It was fear against fear. You see, this was a chess match of global superiority, and it led to the Sputnik crisis. And as many of you probably know, this is really what triggered the space race and the formation of NASA on October of 1958 under Dwight D. Eisenhower. Now, before we continue any further on this talk, I would be remiss if I didn't pay homage to Laika. She was the first living creature to ever orbit our planet. She was sent aboard Sputnik 2, which launched a month after Sputnik 1, and she passed after only a few orbits due to an overheating malfunction. As a dog lover, I must say rest in peace, Laika. It's sad to see that she was brought into our human affairs. So rest in peace, Laika. But not so fast, Soviets. The US responded in kind and launched the first US satellite, Explorer 1, on February 1st, 1958. What do you notice? A few members of the team hold the satellite like a trophy over their head. What do you think was on their mind at the moment? Maybe they were pondering, this is a wondrous achievement for humanity. This day marks the dawn of our civilization's quest to expand the bounds of our cosmic understanding. Unfortunately, there was no romantic vision of expansion in space, nor the pursuit of human curiosity alone. And in fact, 2 weeks before the launch, the National Advisory Committee for Aeronautics Director, which predated NASA, probably echoed what they were thinking when he said, "It is of great urgency and importance to our country, both out of consideration as our prestige as a nation, as well as a military necessity, that this challenge, i.e. Sputnik, be met by an energetic program of research and development, i.e. NASA, for the conquest of space." You see, Explorer 1, which model you see here, was a geopolitical sword. Make no mistake, it was an instrument designed to show superiority. If this was a game of wins and losses, what were the stakes? If space was to be conquered, do you envision much care and foresight would be instilled into such a campaign? Now, of course, in the decades since its inception, NASA has really blossomed into a great resource of scientific information, as well as wonder and curiosity. But it's important for us to acknowledge that its inception and the motivation for it were far less benevolent than its aim today. And thus began a new era of human-engineered instruments beginning to orbit our planet. At the time, our local space environment probably looked something like this: serene, calm, and still. But what type of environment could this become with a lack of global regulation amalgamated with a strong collective impulse to show nationalistic dominance? And so let's get to the heart of the space race and where it likely culminated. You see, after Sputniks and Explorer, the US and the Soviets were trading blows until the Apollo 11 mission, which all of us should be familiar with. Apollo 11 launched July 16th, 1969. This was the first time ever that humans landed on the moon. How many ancient civilizations from eons ago prayed or envisioned that one day we could become one with the universe and traverse the barrier between us and space, that we could somehow dissolve the boundary between ourselves and this majestic ocean above us? Apollo 11, regardless of its motivation, was a very important moment for all of our species. And several years later, the very familiar Space Shuttle program took off. This is STS-1, which is the first launch of that program. This occurred on April 12th, 1981. And in fact, its 40th anniversary was just 3 days ago. But tonight, I want to bring our attention to the Landsat program and Landsat-1, launched on July 3rd, 1972, which actually happens to be the same month and year that the space race officially ended. During this launch, NASA cracked the sky and sent one of 8 satellites that are a part of the broader Landsat program, which actually still runs today. And it's the longest running satellite program that takes Earth imagery, with Landsat 8 launching only a few years ago. This was a big transition. We were beginning to not just use spacefaring missions for militaristic purposes, but Landsat was actually motivated by scientific applications. Based on the images of Earth we got from the moon, we were compelled to understand our Earth's imagery, to understand its topography and the natural processes of our planet. But also with Landsat was a mark of a transition point. We were not just launching instruments, but we were devising programs to launch suites of instruments. We were now launching multiple units of hardware into space. And over many decades, the notion of launching a copious amount of satellites led to the miniature satellite, which was really birthed in 1999. You see, these objects were designed to be easy to build, to be small, about the size of a loaf of bread, as you can see here, and to be a fraction of the cost of these larger satellites, some costing under $50,000, which of course meant you could have graduate students build them. And you're seeing here Dr. Chris Moore, who's a CU alum and a dear colleague, and he's holding in his hand one of the CubeSats, which is probably the most popular flavor of miniature satellites, in his hand. And these are less than 3 pounds, which makes them relatively easy to launch in bulk. And with this development also came the nanosatellite, which is a bit heavier, usually up to 22 pounds, if, say, you wanted to conduct more scientific analysis. But what does this mean for us as a global civilization in terms of our presence in space? And to better understand that, let's look at the total amount of nanosatellites, which are up to 22 pounds, and CubeSats up to 3 pounds, launched since their inception. Now, I want you to pay attention to the 2 top curves. The blue traces all nanosats launched, including failures, and the green below it traces all CubeSats launched, including failures, since 1998. What we really see is right about 2010 to 2012, things are starting to rise, and then we see an exponential explosion. As of January 1st, 2021, nearly 3,500 miniature satellites, CubeSats and nanosatellites, have been launched. So we're really beginning to up the antes here and to launch far more instrumentation into space. But you might ask, what about all satellites, not just the smallest? And to get a better sense of that, let's take a look at this figure. This is provided by the UN's Office for Outer Space Affairs. Now, it traces right around the beginning of the space race, so the late 50s, all the way up to about 2020. What do you notice? So first, let me define what we're looking at. The blue or teal colored data points are all of our non-commercial missions. These are civil agencies, universities, military, and the yellow are commercial missions. So these are private corporations launching. And the red, of course, are unregistered objects. So these are objects that have not yet been acknowledged in our systems. So as we continue our timeline, around 2010 and beyond, you can see an explosion of launches primarily due to commercial missions. and unregistered objects, which, if you ask me, is kind of concerning that we don't fully know at the time of launch exactly what each object is in our systems. So what you see here, like I said, is an explosion of launches. And in fact, since Sputnik 1, nearly 9,000 satellites have estimated to be launched into orbit, with some estimates placing this number closer to 11,000 satellites. Of these 9 to 11,000, roughly 5,000 still remain in orbit. Of these 5,000, only about 3,000 are currently operational. So commercial missions are dominating our orbital space, as you can see. This is the point where we must discuss Starlink. And I'm sure many of you have heard of Starlink. It's a $10 billion SpaceX project based on Elon Musk's vision of bringing global high-speed broadband across our globe. And it's already been approved by the Federal Communication Commissions. It is a mega constellation of satellites. And when I say mega constellation, I am not exaggerating. The company is hoping to launch tens of thousands of the 560-pound satellites which comprise the Starlink system. At the time of this talk, 1,200 are in orbit, and they're usually launched in batches of 60. We're talking about 30 to 40,000 satellites that will be launched in the next decade. I can already envision a future where the word constellation makes references to the brilliant nuclear furnaces, which we know as stars, seem antiquated. For future generations, will that twinkle in the dark night sky merely emanate from the sun's reflection off frigid objects in our planet's orbit? But let's take a step back. We've been very focused here on a very narrow window. Let's take a look at the global participation in our spacefaring enterprise. What about all of the other nations on our planet, aside from just the US and the Soviet Union? So this map is showing that in 1966, a few countries are involved. So what you see here are the solid orange countries are countries that own satellites. The countries with a dashed darker orange are space launching countries with satellites. And as you would expect in 66, the US and the Soviets dominate. And somehow France is in the mix, which I still don't know why. But let's fast forward to 2020. We can see a blossom unfold. More and more countries are participating as the utility of satellite expands. In this new age, we're going beyond purely militaristic applications, like I showed with Landsat. You see, satellites can now be used for astronomy. We can study distant quasars, learn about the origins of our universe, or study our own sun in more detail than ever before using satellites. We can use GPS when we're going on road trips. We can communicate with each other using radio signals. What about weather when you're planning a ski trip? There are weather satellites that help weather models predict when it's going to snow. And commercial purposes I've shown. Broadband internet is just one of many. Think about Dish Network when you get satellite TV. And space stations, of course, the International Space Station, or Earth monitoring like the Landsat program. But if you remember, astronomy has long been interwoven across many ancient cultures since our human history. Vital contributions have come from the Chinese, the Egyptians, Mesopotamian, Greece, Middle Eastern, Indian. Across the entire globe, it's been a global participatory effort. Do you believe our current representation in space reflects this rich and diverse history? While the amount of countries with satellites has increased, which is the dark orange, the amount of countries with space launching capabilities has only gone up marginally. And it's a question I hate to ask, but which country or countries dominate Earth's orbit? does this image reflect a global alliance to explore space? And if there is no global partnership in place, what sense of global responsibility exists within our local space environment? If this is indeed the state of affairs, does one nation or many have more responsibility to act more diligently? Maybe there's another global resource closer to home that can teach us the importance of collective responsibility. Our very own ocean, one of many, calm, serene, and still, despite its natural rhythmic oscillations. But what happens when a global resource like an ocean is not taken care of? What happens when we contaminate our very home? And is it possible that such negligence could grow and reach? What impact could the launches since Bumper 5 and MW 18014, what impact could the launches since then had on our local space environment? And so let's take a look at Gravity, which I actually watched this morning. This is a film with George Clooney and Sandra Bullock, and let's live vicariously through Sandra Bullock. I've shown the rapid increase in spacefaring instrumentation, but what are their waste products and what threat do they actually pose? Is space junk a legitimate concern? Could something like what we see here happen to our astronauts that are currently in space? Well, to determine this, it's very helpful to understand that not all satellite orbits are created equal. Specifically, there are three primary orbits around our planet. There's low Earth orbit, medium Earth orbit, and geostationary orbit. For the low Earth orbit, the altitude here ranges from about the surface to 2,000 kilometers up. And as Jeremy is showing, you can see this region with the lines around our globe. So this extends up to about 1,250 miles, which is roughly the distance between Denver and San Francisco. And it's where the ISS orbits at about 400 kilometers. Now, low Earth orbit is probably the most important region for our talk tonight. It's where 63% of all operational satellites occupy. It is estimated that 20,000 objects, including satellites and space debris, are crowding this environment, some traveling at 17,000 miles per hour, which for reference is about 6 times faster than a fighter jet. And it's capable of producing, as you can imagine, enormous kinetic energy. This is where all of those Starlink satellites will eventually orbit. So why do we keep sending objects to this crowded region? Well, there are a few strategical reasons. The first being it requires the lowest amount of energy to place a satellite here. It provides very high bandwidth and low communication latency. And of course, satellites and space stations are just simply more accessible and easier to service. As we expand further, Jeremy's going to now show us medium Earth orbit. And it's a bit further out. It's about 20,000 kilometers or about 12,500 miles from the surface of our planet. Only about 6% of all operational satellites are in this orbit. Most importantly, as many of us use daily, are GPS satellites. So they occupy the medium Earth orbit. Extending further, and you might have to squint for this one, we're going to show you where the geosynchronous orbit is, which lies about 36,000 kilometers or about 22,500 miles from the surface of our planet. It's the very faint ring that you see. Now, for the geosynchronous orbit, mostly communication satellites occupy this region. And a primary benefit of that is that they don't have to rotate during their orbit. You see, these objects that are in geostationary orbit are synced with the orbital rate of our own planet. And the remaining 2% of satellites, so about 29% of operational satellites are geostationary, and the remaining 2% are in various elliptical orbits. Now, I also want to touch very briefly on what is known as the graveyard orbit, which is also called the junk or disposal orbit. This region lies slightly above the geosynchronous orbit. And as we will uncover, it's a temporary solution to a much larger problem of what we do with satellites that are no longer useful for us. So, as I mentioned, low Earth environment is becoming extremely crowded due to the massive population of objects in this orbit. And what we're seeing here are the orbital debris that occupy this region that we can track. And one of the biggest fears is what can be known as the Kessler syndrome. So the Kessler syndrome is a theory that small particles, particularly in low Earth orbit, can grow in size by striking other pieces of small debris, and thus increasing the probability of striking more matter and growing in size. In layman's terms, it's the snowball effect. But at this point in the talk, I haven't actually defined what space debris is, nor its sources. So let's do that now. So there's the obvious retired rockets and non-operational satellites. But beyond just non-operational satellites and rockets, there's smaller pieces. So would you be surprised if I told you that astronauts have lost a camera, pliers, a lock bag, a wire tie, and even a spatula in space? I have a very serious question. How can one make space eggs without a spatula? And in addition, while minuscule in size, things as small as paint specks can be a real hazard and produce space debris. Consider that these objects travel nearly 20,000 miles per hour. Another concern is, say you have a dead satellite or rocket with some additional fuel or propellant left. Well, of course, the sun is a very warm object, and its radiation can cause an explosion or a rupture of these vessels. And so that can produce much more space debris. So let's take a look at how some space debris is actually produced. So what we're going to see in this video is a very standard rocket separation. Boom. In that instant, thousands of new pieces of space debris have been generated in a very routine procedure. Despite their size, the kinetic energy is most relevant for us. And so let's analyze the numbers. Let's look at it in totality. Let's consider the European Space Agency. They calculated that the number of space debris currently being tracked is about 28,000 objects. The number of breakups, explosions, collisions, or events due to space debris, over 560. The total mass of all space debris is estimated to be over 9,000 tons around our planet. But let's look closer in. Let's consider statistical models. These models suggest that there are 34,000 objects greater than 10 centimeters, which is about 4 inches. Nearly 1 million objects between a centimeter and 10 centimeters. And between a millimeter and a centimeter, 128 million objects that we consider space debris are orbiting our planet. But what are the actual risks? Well, as for those of you that know me, as a hopeful astronaut myself, this is particularly relevant for me. And what better place to start than the International Space Station? You see, the ISS, as I mentioned earlier, is in low Earth orbit, which is only about 400 kilometers up for its actual orbit. What physical protection does the ISS have from space debris? And soon we'll be right upon the ISS. The primary protection is a physical barrier. It's like a bumper that protects the interior from small objects. However, as you see, in 2016, a 7-millimeter diameter chip was made in the ISS's cupola by a sub-millimeter object that somehow found its way through. If a sub-millimeter object can produce a crack like what you see, what can any size larger do? And for reference, research estimate that it may only take a 10 centimeter or roughly a 4-inch size object to destroy a satellite. It's also important to consider that there is no such protection for those solar panels you see. Now, during its lifetime, the ISS, which was launched in 1998, has had 28 collision avoidance maneuvers. These are performed anytime there's a 1 in 100,000 chance or greater that the ISS could be impacted by space debris. There were 3 collision avoidance maneuvers in the last year alone. Now, if all else fails, and we have a scene from Gravity, there is a last resort, and it's called a shelter-in-place protocol. This requires astronauts to seek shelter in usually a capsule docked on the station. So you might be wondering, is this just theoretical? Has there actually been a true collision in space due to space debris? And in fact, there has. In 2009, we had the first hypervelocity collision between 2 satellites. The expired Cosmos 2251 satellite, which was launched in 1993, collided with the Iridium 33 satellite, which was launched in 1997. They collided with a relative speed of 26,000 miles per hour. The collision created thousands of pieces of additional space debris. And in fact, a piece of debris came within 390 feet of the ISS, which for reference is about the length of the ISS. So this is very close to our astronauts up there, and it actually caused a shelter-in-place procedure. So it's important to acknowledge that this is an actual living space environment. There are people that live in space. Scott Kelly, for example, spent about 340 days in space. Mitigating space debris isn't just about cleanliness. It can actually translate into survival. Imagine making breakfast, hopefully with an available spatula, and the possibility is realized that an object traveling nearly 20,000 miles per hour could zoom through your kitchen. There are real-life hazards for space debris. But I want to return to Starlink. Starlink is going to be our mega constellation, and so it's important to focus on this for a little bit longer. And we've explored a lot about the local space environment, but we haven't discussed the consequences of space debris from Earth. And similar to space habitability, as an astronomer, astronomical observing is something that is also very dear to me. What you'll soon see on your screen is the deployment of a typical batch of 60 Starlink satellites. Talk about deploying in bulk. Is it possible that we approach a day when the number of visible satellites is greater than the number of visible stars? When you gaze up on a cool summer evening, with a soft breeze gently whispering eternity, will that glimmer just above solely be metal and glass orbiting our planet? Even if all of these satellites are painted black, obscured light cannot be recovered. When a source is blocked, that information is effectively lost as the light bounces back into space. Now, I can't give this talk without bringing up a few truly noteworthy incidents. These incidents are Project Westward and the anti-satellite missile tests. These were two events that produced the largest amounts of space debris in our entire recorded human history. First, Project Westward. During the Cold War, the US feared, again, fear seems to be a common theme during this time, that the Soviets might compromise their means of communication, which at the time relied upon undersea cables or bounced off the natural ionosphere. So they decided to launch a ring of 480 million copper dipole antennas, roughly an inch long, into orbit to strengthen global radio communication. And as it turned out, this technology was shortly shelved due to the creation of the modern communication satellite. To this day, clumps of dipole antennas that were not properly deployed still remain in orbit. And let's fast forward to 2007, when the Chinese wanted to test their anti-missile technology. They intentionally destroyed their own satellite, and in the process created over 150,000 debris particles. 150,000 debris particles from a proof of concept test. So where does this leave us collectively? Who will save us? Some of you ask. Well, the Combined Space Operations Center, part of the United States Strategic Command Center, formerly the United States Space Command, which is now the United States Space Force, is one of the primary agencies tasked with monitoring space debris. And NASA's Orbital Debris Program also helps with this effort. Collectively, they track over 8,500 objects larger than 10 centimeters in low Earth orbit. And this is specifically designed to help avoid collisions with their valuable satellites. However, a limited Arecibo study suggested there could be over 1 million objects larger than 2 centimeters, which are too small to be visible from Earth-based observatories. And in a grander sense, tracking these objects is just that. Does it fundamentally address the production of new space debris? I also want to acknowledge that agencies like NASA do have strict deorbital guidelines. So after, say, 3 or 4 years, some missions are forced through procedures and guidelines to deorbit their instruments. And companies like SpaceX do use reusable rockets to limit the production of new space debris. However, these approaches have not been globally adopted and thus limit their global efficacy. I told you I would come back to it, the graveyard orbit or the orbital graveyard. What about this region? Well, as I mentioned, this orbit lies further out, and most objects can persist here for millions of years. But there are increasing numbers of satellites being launched, of course, and more are occupying this orbital graveyard. An analogy I like to consider is stuffing all your clutter into the closet. Eventually, you're going to have to deal with it. And of course, there are monetary and physical constraints. So if you have a satellite with a very specific mission, if you require it to maneuver to a new orbital path, then that's going to require additional propellant, mission logistics, etc. And also increases the probability of striking other objects. What about physical removal? Let's just get up there and manually get it down or send it down. So for this solution, a few ideas have been proposed. There's the laser broom, there are space nets, and there are space harpoons. So the laser broom is a cool concept. You pulse a laser essentially in this model, and the laser beam powered propulsion induces whatever object you're striking into a lower orbit with the hopes of forcing re-entry And if the object is small enough, hoping that it just burns up in the atmosphere due to the friction we discussed in the mesosphere. But what about the larger objects? What about the possibility of striking a populated area? And for the nets and the harpoons, which essentially skewer the space debris and tether it in, this only works for the largest objects. And again, do these solutions, potential solutions, actually address the question of, are we limiting the production of space debris? In all likelihood, these rescue crafts may be hit by space debris and make matters worse. What we're dealing with truly is an open access issue. It's like a highway or a fishery or an ocean or our atmosphere. And while there's no immediate solution, CU alum Akhil Rao might have an idea. He is an advocate for a fundamental change in the psychology of producing space debris. If someone's littering in a park, what's a good way to de-incentivize this behavior? Usually going for an offender's bank account seems to work. People seem to sit upright when you mention money. What Akhil has proposed is to charge satellite operators, sort of like a carbon tax. This would factor in the collision risk of their instrumentation, as well as the likelihood of producing more space debris. This could incentivize rapid deorbit. But I do want to touch on the prospect of deorbit. Might we just be producing or exchanging one debris for another? A single large-scale mission with huge rockets can produce 10, 20, 30, 40 tons of space debris that ends up in the ocean, some which may still contain propellant. So we have to be careful that we're not just exchanging the environment of the debris. Now, the estimated cost would be about $235,000 per satellite by the year 2040. But some natural questions arise for me, at least. Where would the money go, and who would regulate such a system? How could we ensure international cooperation? Who should be in charge? Would one country have more power and influence over another? In the words of Carl Sagan, who speaks for Earth? Maybe the first step is to revisit our existing global treaties and to ensure that they're fair and balanced, and that they're indifferent to the wealth or power of nations. The most important thing is to mandate direct and immediate action. And if all else fails, there's more work from CU students. So CU's Shayla Musler says, hey, if that space debris is going to be up there anyway, why not use it to monitor space weather, such as solar emission impacting our atmosphere? And consider that a lot of the space debris are very high area to mass ratio objects. So imagine a spent rocket. It's a huge object, but doesn't have a lot of mass. So you can very precisely measure the amount of drag on such an object. These observations could be helpful because they can help us monitor collision courses, build better prediction models, and reduce unnecessary movements of satellites, and also just understanding space weather better. But ultimately, hopefully I've shown this evening that we are at a crossroads. Technological innovation, like the advent of the automobile or power-driven machines or satellites, seems to be at odds with our willingness to execute mindful discipline and oversight, which can result in environmental crises like global warming or polluted oceans or space debris. For example, with Starlink, having stable internet across the globe is immeasurably valuable, particularly for impoverished nations. But it also produces large amounts of space debris and imposes limitations on our observing of the night sky, which again can unite all of us, from the oldest to the young. The night sky, at least to me, reminds us of our collective origins. Further, weather, communication, GPS satellites are extremely useful. They offer extraordinary convenience. CubeSats and nanosatellites are affordable. They deliver quality science. But what is the true cost? A recent study predicts the growth rate of space debris may overcome the natural decay rate of the space debris that exists within 50 years, and that the low Earth orbit could be inaccessible for thousands of years. Our oceans and our atmosphere have offered us seeds of wisdom. As we venture to other planets and other moons, can we absorb these teachings and explore responsibly? As of right now, nearly 500,000 pounds of materials have been left by humans on the moon. 54 probes have collided into its surface. Moon buggies linger. On Mars, there have been 18 spacecraft missions that have orbited the planet, and 8 are currently active, less than half. We now have more space debris around Mars, which is over 30 million miles away at its absolute closest approach, than we have active instruments. We have to ask ourselves, what are we doing? In the quest to explore, to conquer, to find life, or to dominate, as we did early in our spacefaring quest? What history are we truly creating here? What kind of wake are we leaving in our path? But that being said, I am always an optimist. We are still in our spacefaring infancy. Like global warming and ocean pollution, we are still capable at any moment of awakening and creating, in the words of Eckhart Tolle, a new Earth. We exist on the only rock we know that can definitively sustain life, so our actions are immeasurably vital. It's been less than 80 years since we first ventured beyond that Kármán line and into space. That's less than one human lifetime ago. It's not too late to reverse this course. And so I will close with this. The glowing sun shines intensely this morning. A new dawn casts vibrant light onto the fatigued dreamers. The cosmic shores compel our species to wander further. While uncertainty permeates the collective mind, the urge to explore remains ingrained. The desire to stretch our cosmic perspective and to push the bounds of familiarity have burned fiercely throughout the dark and frigid night. How will we decide to journey forth on this horizon that beckons? Thank you.
All right. Awesome talk, Jimmy. Thank you so much. So if people have some questions, they can leave them in the chat below and I'll read a few out and we can get Jimmy's opinion on them. So it looks like we already have a few. So the first one I see here is, have we had instances of space junk hitting our space vessels or satellites, and have we had any plummet back to Earth after being up in space?
That's a great question. So in terms of our major satellites, we have not had any severe collisions other than that 2009 incident. When there is space debris that is produced, then yes, there is a likelihood of some of the smaller components deorbiting and then burning up in our atmosphere. But as of now, we have not had any true catastrophes in space, which is why it's so important to be preemptive.
All right, this next one is, can you comment further on the danger posed by potential space warfare as shown with the 2007 Chinese anti-satellite test you mentioned?
Oh dear. I don't know how much I want to venture into that, but the space race, in a sense, has become global. You know, the quest to explore Mars and other regions of our local space environment has certainly grown. You must also consider which nations are naming features on certain planets or staking out territory or occupying with instrumentation. So it's very important that we're very thoughtful in how we adventure forth. Ownership in space. Generally, territory leads to conflict. So it's something we should keep in mind.
And then also there's the question, do you know how the spatula got loose?
I have no idea. They do routine spacewalks. Maybe they left it in one of the bags. It's kind of embarrassing though.
Maybe it was an
All right,
engineering
so
problem.
yeah, if anyone else has any questions, we have a few more minutes, so leave those in the chat.
Yeah.
I have a question for you, Jimmy. So you want to be an astronaut, you're an astrophysicist. With all of that in mind, and just being a citizen of Earth, do you have like a single favorite satellite or anything up in space right now that you just think is like so cool?
I'll always be a fan of Hubble and James Webb when that launches. Satellites are extremely valuable. And, for astronomers like myself, that is their source of livelihood. So, I find them immensely valuable. It's just important to be cautious with the rate of our launches and tracking down what is up there.
Okay, what obligations do nations have to report defense satellites? Do you know?
That would probably be in, there's the UN Outer Space Treaty, and I'm sure it's outlined there. So the thing with treaties is there's one thing to have literature, and then there's one thing in terms of like practicality and ensuring that there are true consequences for breaking agreed upon language in these treaties. And so there's the question of enforcement, which I am not fully aware of, but it is a concern. The militarization of space is very much concerning.
Okay, next one is, do you think that Starlink is an overall boon, or does its cost outweigh the benefits?
I don't think that the benefits justify its impact. 30 to 40,000 satellites in the next decade is very ambitious, and I think could set a dangerous precedent. And many astronomers have expressed their frustration with their astronomical observing, and there have been, mitigation efforts, but the issue is still not resolved of how do you prevent these objects from distorting views of the night sky, particularly from ground-based telescopes. And there's also the issue of just producing so much hardware in space. I think there are a lot of ground-based solutions that can be pursued to provide global internet. And maybe we should consider a joint effort to reduce just the sheer volume of Starlink satellites.
All right, so it looks like there's 2 more questions in the chat on things we haven't talked about yet. So the next one is, are there any talks among nations and companies to share satellite functionalities that might mitigate space debris?
That is one of the most direct solutions to reducing the amount of hardware we have in space. And the amount of global partnerships is limited. So the ESA and JAXA, Japanese Space Agency, European Space groups, and NASA do collaborate on a few missions, but there certainly is a lot more room to grow in terms of a partnership. There's a lot of redundancy. If one country says, we want to go to Mars, we want to have weather satellites, we want to have communication satellites, and many are achieving the exact same science or collecting similar data, then we're just producing unnecessary hardware in space. So cooperation is generally a good rule of thumb there.
All right. Ooh, another one popped up. So I'm going to go out of order to keep on this track while you're on it. If we continue on the same business as usual with spacecrafts being launched, what will the sky look like in 100 years?
That's a scary thought, it's a scary thought. Just look at the explosion of technology. And even in the past decade, the explosion of satellites, technology grows exponentially. And as more companies get involved, really the door has just now been opened by SpaceX and Blue Origin, and Dish Network has been up there. But we could see an extremely crowded space environment. And I fear that, the day where I go out, in the Rocky Mountains and I count more satellites than I can identify stars. So I would say it's a real concern. And as I mentioned, a recent study said that within 50 years, the growth of space debris could outnumber the natural decay of it. And if low Earth is completely congested, that could limit our access there. And keep in mind, if we're launching to Mars, you have to go through low Earth orbit, And so low Earth orbit is really, it's like the skin of an apple around our planet. And so if we obscure and make that a hazardous environment, then again, the only rock we know that can sustain life may be enshrouded due to our own actions. So right. I think it's scary.
Okay, and so this last question here, this is the last one I see in the chat for now. Mm-hmm. This one is, what data are astronomers and astrophysicists most excited about getting from JWST? And so for anyone who doesn't know, just before Jimmy goes into this question, right. JWST is the James Webb Space Telescope, and it's kind of the mm-hmm. successor to Hubble in some ways. Mm-hmm. It's the next big one that NASA is launching. Its mm-hmm. launch date is currently scheduled for Halloween, so fingers crossed it makes it up there. And this one is actually not orbiting Earth the way Hubble is. It's going to fly out to a point in space and basically follow Earth around the sun. So that's like a little summary of JWST for anyone watching who doesn't know. But now I'll toss it over to Jimmy for what data are we most excited for?
So that's going to vary on which astronomer you ask, but I can't wait for the infrared data. So this offers us the ability to see heated gas and dust around supermassive black holes. And so this is very exciting for me that we can peer further into distant galaxies. So I'd say the infrared instrument is one of my most, one of the features I'm most excited to see at work.
Yeah, and as Jimmy said, it's infrared, so we can see this heated gas. So hopefully we can also see how planets form around other stars. And hopefully we can also see some of the very first galaxies is another goal of the telescope. So I would agree, it depends on who you ask, but those are some other pieces of information to expect to see over the next few years. All right, so thanks everyone for coming to this talk, and thank you, Jimmy, for such a fantastic presentation. If you are a CU student watching, you can learn more about us on CU's Buff Connect site or shoot us an email at scienceunderthedome@colorado.edu. And keep an eye out on this YouTube channel where you can see our fabulous navigator, Jeremy, doing some other shows as well. So thanks again, Jeremy. Of course, so keep an eye out here and as well on Fisk's social media platforms for more information about our plan for the fall talk series through Science Under the Dome. And thanks again for joining us. Have a great night.
Thank you so much, everybody. Take care.